Okay, so topic 23, exponential functions and applications. We're going to go over the characteristics of exponential functions and then look at some applications. So for characteristics, we have a lot of definitions here. So an exponential function is a function in which the independent variable x appears as an exponent. It is represented by this function, f of x is equal to a times b to the x power, where a is the y-intercept and b is the growth or decay ratio. That's the important information in that first part. There's different types of exponential functions. The first type is the natural exponential function, which uses Euler's number and is written as f of x is equal to e to the x. So e in this case is a number, just like pi is 3.14, e is, I want to say 2.47 something. Exponential growth, so if our b value is greater than 1, that tells us we're using a growth rate of 1 plus r. And the function could be written as f of x is equal to a times 1 plus r to the x power. And then opposite with decay, if it's less than 1, our b value is 1 minus r, and we get the function f of x is equal to a times 1 minus r to the x power. Okay. Last thing are the asymptotes. So remember we learned about the asymptotes in the couple notes back. Both asymptotes here, y is always equal to 0. Okay, so that's the only thing you have to remember here. Y is always equal to 0, and you'll see why when we start looking at those graphs. Okay. So in these examples, we're going to be drawing a rough sketch of each function. So starting with the first function, we have f of x is equal to 3 times 2 to the x power. Remember, our standard form looks like f of x is equal to a to the b to the x power, where a is the y-intercept and b is the rate, whether that be growth or decay. So part A says, is this a growth or decay? So look at our b value, which is 2. Is 2 greater than 1? Yes, so it is a growth. It's a growth because 2 is greater than 1. Okay. Then it's asking for our y-intercept. Remember, our y-intercept is always that first number. So what's our y-intercept here? 3, so 0, 3. Okay. Part C says, what's the asymptote? We said it's always y equals 0. Okay. So if we were to sketch this, that y equals 0 is right here. This tells us that our graph is not going to go past that y equals 0 line. So it's not going to go past it. Okay. The first thing we plot when we're sketching these graphs is the y-intercept. So the y-intercept is 0, 3. So first plot the y-intercept. And then you just look at whether or not it's a growth or if it's a decay. So since ours is a growth, our function is going to be going up. And that's it. That would be a sketch of our exponential function. So the only difference is if it was a decay, our arrow would be pointing down. It would be going down into the right direction, but would not go past that y-intercept. So you first plot the y-intercept, then you draw the rate, whether that is a growth or a decay. Any questions on number 1? Okay. Number 2. So now looking at this function, is this a growth or decay?
Decay.
Decay. Why is it a decay?
Half is smaller than 1.
Good. 1/2 is smaller than 1. What is our y-intercept? Perfect. 0, 4. Our asymptote is always y equals 0. We got all our information. Now we graph. What's the first thing I'm going to graph here? Good, the y-intercept. I only draw this line first just to emphasize that we don't go past it. Okay, it's not something you have to do. So graphing my y-intercept at 0, 4. Now I draw my rate. So since I have a decay, which direction am I going? Up or down? Down. Okay. And remember, these are just rough sketches. If you're ever asked to just graph it, which I don't believe we do in these notes, the only thing different you would have to do is create a table, and that table would give you exact values, and those exact values would help you find the exact points on this to make it more accurate. Okay. Okay, number 3, is this a growth or a decay? Growth because, good, 3 is larger than 1. What's the y-intercept? Good. 0, 1/2. Or you could write this as 0, 0.5. Either one. The asymptote is always
0.
y equals 0 because we don't go past that line. And then the first thing I'm going to graph is what?
Your y-intercept.
Y-intercept. So I have that 1/2. Okay. And since this is a growth, this is going in what direction? Up. Okay. Okay, number 4. Is this a growth or a decay? Growth, because 2 is greater than 1. What's the y-intercept? Good, 0, 4. Our asymptote is always which equation? Y equals 0. And the first thing we plot is the y-intercept. So I'm going to plot the 4. And this is a growth, so it's going in what direction?
Upwards.
Up. Okay. Okay, go ahead and take a moment and try 5 and 6. You're answering those same questions, and then you're sketching your graph, and then we'll go over them. So on the final, you'll have at least one of these questions where you just have to sketch the exponential function. Okay, so for number 5, is this a growth or a decay? Growth. 5 is greater than 1. Our y-intercept, you should have got 0, 1/2 or 0, 0.5, whichever is easier to graph. Should have got y equals 0 for your asymptote. And then sketching the graph, once I plot my point of 1/2 on the y-intercept, my growth tells me I'm going up. For number 6, did you get growth or decay? Decay, because 1/2 is less than 1. Our y-intercept, you should have got 0, 5, because it's that first number. And the asymptote y equals 0. So when I plot my y-intercept of 5, since this is a decay, it's going to be going in what direction? Down. Okay. And remember, we never go past this y equals 0 line. And that's because of the asymptote. Okay. So now that we looked at how to graph these examples, an important part of exponential functions is that it pops up a lot in applications, so real-world problems. So we're going to go down to that as the next part. Okay. When we see exponential functions in real-world problems, we see a lot of this in problems that state, you invest this much over this amount of time, how much do you have? So those business-type applications. So the first formula we're going to look at is the compound interest formula. So here's the formula, and then in this sentence, I label what everything is. So for example, A is the final amount, P is the principal, R is the rate, and N is the total number of compounding times in a year, where T is time. Okay? So they vary per problem, depending on what information is given. The next formula is the continuous compound interest formula, which is given by this formula here. And again, I label what each part is. So A is the final amount, P is the principal, R is the rate, and T is the time. And then lastly, the simple interest formula. And again, where A is the final amount, P is the principal, R is the annual rate, and T is the time. So these variables all mean the same thing, just depending on what problem is depending on which formula we're going to be using. But for the sake of this course, I'm asking you, use the simple, use compound annually, use compound monthly. So that tells you what formula we're going to be using. Okay. So I'm not going to give you the formulas, but I will tell you which formula to use. Okay. So in number 7, it says, if you invest $800 for 5 years at 2.5% interest, how much would you end up how much would you end up with interest if you use a simple interest formula? So remember, the simple interest formula is A is equal to P 1 plus RT. Okay, we're trying to find A. We're trying to find that final amount. How much would we end up with? Okay, so principal is whatever we start with. So how much did we start with? 800. So I'm going to label it in the problem. So 800 is P. Our rate was what number? 2.5. But we have to take that 2.5 and we're going to have to put it into a decimal.
2.5.
So 2.5 is just the percent. So 2.5 is this percent. If we are going to turn it into a decimal, we have to move the decimal place 2 places to the left. So that would be the same as dividing by 100. So we would get 0.025. Okay? So even if your interest is already a decimal, if it's in percent, we have to turn that percent into a decimal by dividing by 100. So this is our R value. And then our T is what number?
5 years.
5, that's our time. Okay, so now plugging everything in, I have A is equal to 800, parentheses 1 plus our rate, which is 0.025, times our time, which is 5 years. And what you could do is you could type this entire thing into your calculator, as long as you're including those same parentheses. So 800 parenthesis 1 plus 0.025, parenthesis 5, and then 2 parentheses to close. And then you should get A is equal to 900. So go ahead and test it on your calculator. Make sure we're typing that in correctly. Bless you. Bless you. And then if you don't want to type this entire thing in, you could just, find out what this value is, add it to 1, and then multiply it by 800. So this is saying in 5 years at 2.5 interest, they earned an extra $100 in 5 years. Okay. Now we're going to look at compounded annually. So compounded annually, we're using the compounded formula, which is A is equal to P 1 plus R over N to the power of N T. Did I have that formula? Yeah, it was that first formula there, compounded interest formula. Okay. So we have everything labeled except that N. So if we go back to our formula, N is the total number of compounding times in a year. So it's how many times we're compounding a year. Since this is annually, N is going to be what number? 1 time. Yep. So N is equal to 1. So we're going to plug in all our same numbers. So A is equal to P, which we said was 800, times 1 plus our rate, 0.025, divided by 1 to the power of NT, so 1 times 5. So all the same numbers we used in the problem, plugging it into a different formula. Go ahead and type that into your calculator. And for this one, we should get A is equal to 905.13. Remember, if you can't get this in your calculator, just use that PEMDAS that we learned in the beginning. Do the inside of the parentheses first, raise that to the exponent, multiply by 800. Okay, next one, compounded monthly. So again, we're using that same formula as above because it's still the compounded formula. But in this case, N is going to be what? How many months are in a year? 12. So we're plugging in all our same numbers except N is now 12. So A is equal to 800 times 1 plus 0.025 divided by 12 to the power of 12 times 5. So same as above, instead of n equal 1, we're now plugging in n equals 12 because there's 12 months in a year. When we compound monthly, we should get the answer A is equal to 906.40. Remember, since we are talking about money, we are only doing 2 decimal places. Okay. Next one, same formula, but in this case, what is going to be our n?
7.
Think of how many weeks are in a year.
4.
52.
4 weeks in a week.
So n is equal to 52 now, because when we think of compounded, we think of whatever word is next, how much of that is in 1 year? So there's 52 weeks in a year, so our n is now 52. So all our same numbers, the only number that changed was n. So A equals 800, 1 plus 0.025 divided by 52, and then 52 times 5 as our exponent. This one didn't change too much from the next one because you should have got A is equal to 906.49. So it changed by 9 cents. And again, on your own time, I would just practice putting these into your calculator and make sure you're getting the same answer as me. Okay. Next one, it's still compounded, so we're using the same formula. But now it says compounded hourly. So how many hours are in a year? It's okay, something you'll probably have to look up. There are 8,760 hours in a year. Okay. If on the exam I'm asking you to compound hourly, I will give you that n value. Okay. So then again, the only difference is n that's changing. So A is equal to P, A is equal to 800, 1 plus 0.025 divided by 8,760, raised to the power of 8,760 times 5. So again, the only thing that changed in this equation was our n value. Okay. When you plug this into your calculator, try putting these extra parentheses around here. And that forces your calculator to do the divide part before the adding part. Here we should get A is equal to 906.52, so only a 3-cent difference from the formula above. And then lastly, this is asking us to compound continuously. So that formula was A is equal to P times E to the power of RT. Remember, E is a number, so you should see that on your calculator somewhere. So we have A is equal to 800 E to the power of our rate, which was 0.025, times time, which is 5. So again, this E value is a number on your calculator. And when you plug that in, you should get the same answer as above, that 906.52. So what this problem is doing is it gave us what we invested, how much time, what the interest is, and it compared every single interest formula. So looking at all of these answers, which formula would be the better one to invest your money in, where you got the most back? Which part in this answer? A, B, C, D, E, F? Yeah, F or E, because they came out to the same answer here. So in this case, it would be better to compound hourly or compound continuously, since they gave us the same amount and it was the greatest amount. Any questions on number 7, where we're just plugging numbers into our formula? Yes.
For E, I just kept getting 800 back in the calculator.
When you type it in, do you have, let's see, this part in parentheses?
E, not F.
Oh, sorry, E. Okay, do you have this part in parentheses right here?
Yes.
And it's still giving you, show me after class and we'll see what's happening on the calculator. Okay, so let's look at the next problem.
Quick question, ma'am.
Yes.
Our N values, for the following questions, also annually, monthly, weekly, hourly, is it also gonna be the same 1, 12, 52, and 8, 7, 60?
Yes. Yeah. Because we're talking about how many times that happens in a year, and that always stays the same. Okay. So looking at number 8, we have to label everything. So it says you have invested $100. So that's our what value? P. Earning a 2% interest, so that's what value? R. And how are we going to turn that into a decimal? Good. 2 divided by 100, so 2 decimal places to the left, so that's 0.02. What is the 15 years going to be? T, our time. And I believe we have everything labeled. So we're doing the same thing we did as the other side, using all the same formulas. So remember, our first formula for simple interest was A is equal to P times 1 plus R times T. So that's A is equal to P, which is 100, times 1 plus our rate, which was 0.02, times our time, which is 15. Okay. Plugging that into your calculator, you should get A is equal to 130, so $130. Okay. Remember, in some of your calculators, you may need the extra parentheses here. Just depends on the type of calculator. Next one, compounded annually. So this is that A is equal to P times 1 plus R over N to the power of NT. Remember, we're using this formula for majority of the questions. The only thing that changes is our N value. So since it says annually, our N is going to be what number? 1. So plugging everything in, we have A is equal to P, which is 100, times 1 plus our rate, which is 0.02, divided by 1, because that's our N value, to the power of 1 times 15. Again, plugging this to your calculator, you may need these extra parentheses here. But since our N value is 1, we don't really need to divide by 1 here. You could just do 1 plus 0.02. For here in your calculator, you should get 134.59. Okay, so we get a little bit more money back compounding annually. Compounding monthly, the only thing is changing is our what? N value, and how many months are in a year? 12, so our N is going to be 12. Okay. All the same numbers except N. So A is equal to 100 times 1 plus 0.02 divided by 12 to the power of 12 times 15. Again, you may need these extra parentheses here, or you may even need the extra parentheses in your exponent. Depends on your calculator. When plugging everything in, you will get 134.95. So again, we're a little bit better than part B, getting a few more cents there. Okay. Now we're compounding weekly, so what value is changing? Our N value, and how many weeks are in a year? 52. So now instead of putting 12 like we did in the last one, we're putting 52. So our formula and then plugging everything in, I have A is equal to 100 times 1 plus 0.02 divided by 52 to the power of 52 times 15. Type that into your calculator. Weekly, we get 134.98. Okay, so it looks like each one we're improving by a few cents so far. Okay. Now we're compounding hourly, and remember I said there are 8,760 hours in a year. So plugging that into our formula, we have A is equal to 100 times 1 plus 0.02 divided by 8,760 to the power of 8,760 times 15. Only changed out that N value. Plugging it in, I get 134.99. So that made us an extra penny. And then what did we notice about F in the last problem when we were looking at comparing E and F?
It's the same as compounding hourly.
Yeah, the compounding continuously gives us the same amount as compounding hourly. So that means when we're doing this compounding continuously equation, we should get the same 134.99. So our formula, A is equal to P times E to the power of RT. We get A is equal to 100 times E to the power of 0.02 times 15. And again, plugging in that into your calculator, you should get the same 134.99. So again, in this problem, the best formulas to use are either compounded continuously or what? The best ones to use, compounded hourly, because they're the ones that gave us the most money. We started with 100. After 15 years, we got a $34.99 increase. Okay. Any questions on the past two? Okay. Another example where we can see this application is in population. So, for example, one of the more popular applications is always the growth or decay of bacteria. So it says the growth of a bacteria colony can be modeled by the function below, where n is the number of bacteria in thousands, and t is time in minutes. So we have n is equal to 25 times e to the power of kt. This says, what is the initial population of bacteria? The initial population of bacteria. Remember, our initial value is always that first number. Excuse me. The first number in this case is what in our formula? 25, but it says the bacteria is in...
Oh, so would it be 25,000?
Good, thousands. So since our bacteria is in thousands, the initial population of bacteria is 25,000. So this is the initial value, but it has to be in thousands according to our problem. Okay. Next one says, if the growth rate is 1% per minute. First, before we continue, 1% would be turned into what decimal for our rate? Yep, 0.01. How much bacteria would you have after 2 hours? Okay, so in this case, our rate is that value k, because notice they didn't identify k in the problem. So this k is going to be our rate. Typically we see that as r, but they could change up that variable for rate for whichever they want. We know that that's rate because if we look at our typical formula, which is that a is equal to p times e to the power of rt, notice how that r is in the same place as the k. So in this case, our k value is the rate. So we're going to start writing our equation. So n is equal to 25 times e to the power of kt. So n is equal to 25e because e is just a number. Our rate is k, which we said is that 0.01. And our time is in minutes. So if our time is given as 2 hours, how much is 2 hours as minutes? 120. So times 120. Okay. So if we plug that into our calculator, we should get n is equal to 83. But since n is in thousands, our answer is actually what? 83,000. So this is saying at a growth rate of 1% per minute, after 2 hours, our 25,000 bacteria went to 83,000. We also know we did that correctly because it says growth rate, meaning your number should be larger. If it said decay rate, our number would be what? Smaller. Okay. Any questions on 9? So a lot of these are just plugging into our formulas. Number 10 says, suppose that 7,000 is invested at an annual interest rate of 5% compounded daily. That right there is telling us what formula we're using. Find the total amount in the account after 12 years if no withdrawals are made. Okay, so that this compounded right here tells us we're using that compounded formula, which is A is equal to P times 1 plus R over N to the power of NT. Let's go back and label everything. What would be our P value? What did we start with? 7,000, so that's P. Let's see. 5% would be our what? Our rate, and how do we turn that into a decimal? 0.05. Remember, divide by 100. Okay. 12 years would be our what? Our T. And then this says compounded daily. So how many days are in a year? Good, 365. So N is equal to 365. Once we've labeled all our information in the problem, we're plugging everything in. So A is equal to 7,000 times 1 plus 0.05 over 365 to the power of 365 times 12. So this one is compounding daily for 12 years. Plugging that into your calculator, you should get A is equal to 12,754.31. So that one made that person a lot of money. Okay. So again, once we label everything, plug it into our formula. Once you plug that into your calculator, this is the answer you get. Since we're talking about money, we always round to 2 decimal places. Okay. Number 11 says Bank A offers a 15-year loan at a rate of 4.5% compounded weekly. So this is A. While Bank B offers a 10-year loan at a rate of 5.75% compounded continuously. If borrowing $4,800, which loan is better? Okay. So we're going to have to set up these 2 equations, one's for Bank A and one for Bank B. Once we have the answers for both, we choose which one is better, first or second. So let's start with Bank A. Bank A says compounded weekly. So that compounded weekly tells us we're using the formula A is equal to P times 1 plus R over N to the power of NT. Compounded weekly tells us our N value is what? 52, because there's 52 weeks in a year. Okay. What is going to be our P value? 4,800, and that's going to be the same for both because that's what we are borrowing. Our rate for Bank A is going to be what decimal? 0.045. And then lastly is our time. Our time is going to be what number? 15. Okay, so I labeled everything for Bank A. I'm going to go ahead and plug everything in. So A is equal to 4,800 times 1 plus 0.045 over 52 to the power of 52 times 15. When I plug that into my calculator, I get 9,424.61. Okay. Now bank B. Bank B says we are going to be compounding continuously. So what formula is that? Good. A is equal to P times E to the power of RT. We already have everything. Oh, wait, no, we don't. This is new. Our P is going to stay the same. Our rate this time is what decimal? Good. 0.0575. And then our time is what in this problem? 10. Our time is that 10. So I have A is equal to 4,800 times E to the power of 0.0575, that's our rate, times 10, that's our time. Plugging that into your calculator, we get 11,371.56. If we are borrowing money from the bank, these are the amounts that we're going to end up paying back. So which one's the better bank, A or B? A, because you don't want to pay, like you would rather pay 9,000 versus that 11,000. So bank A is better because we were borrowing money, not investing money.
Yeah, same.
Oh, okay. Let me double check on my calculator. Okay, yes. Okay, so 8,530.23. Well, in that case, which bank's better? Bank B, because you're paying less. Okay. Everyone still got that 9,000 number for A? Okay. Okay. Now looking at number 12. It says an investment property in 2016 was worth $375,000. If decreased in value at a rate of 3.5% a year, compounded annually, what will its worth be in 2030? So that compounded annually tells us our equation is A is equal to P times 1 plus R divided by N to the power of NT. Okay. So P is our initial investment. So how much did we buy the property for? Okay, so that's our P value. Okay. Our rate is going to be what decimal? 0.035. But it says that this rate is decreasing the value of the house. So would our rate be positive or negative? Negative. So we have a negative rate because it is decreasing the value of our house. And then what would be our time? 14 years, because we started at 2016, we're ending at 2030. So our T value is 14 years. There's 14 years between 2016 and 2030. Okay, and then lastly, what is our N value? Good, our N value is 1 because it says compounded annually. Okay, so plugging everything in, we have A is equal to 30, 375,000 times 1 plus our negative rate, so negative 0.035 over n, which is 1, to the power of 1 times our time, which is 14 years. Okay. Plugging in that into your calculator should get 227,726.54. So this is saying after 14 years, since the value decreased, it decreased from 375 to 227,000. Okay, any questions so far? Number 13 says the amount of plutonium remaining from 1 kilogram after X years is given by the function W of X is equal to 2 to the power of negative X over 24,360. Okay. How much will be left after 1,000 years? So X is years, so where are we plugging in 1,000? In X. So we have W of X is equal to that 2 to the power of negative X over that 24,360. I'm now plugging in 1,000 for X. Okay, and remember this is an exponent, which I would put in parentheses when you put into your calculator. Let me make this 2 a little bigger so you can see that's an exponent. Okay. When you type that into your calculator, you should get that W of 1,000 is equal to 0.97 kilograms. Did everyone get that? 0.97. Remember, I'm rounding to 2 decimal places if it comes out to something greater. So this is talking about a decay. This is a decay function. So it's saying after starting with 2 kilograms, after 1,000 years, we're left with a little less than 1 kilogram. Now, looking at part B, it says how much will be left after 10,000 years. So where are we plugging that 10,000? Into X. So same thing. So we have W of 10,000. Oops. Is equal to 2 to the power of negative 10,000 over that 24,360. Plugging that into your calculator, we get 0.75 kilograms. So after 10,000 years, 0.75 kilograms is left.
It's decreasing slowly.
Yes. Then last problem, we have the function m of h equals 10 times e to the power of negative 0.173h. Can be used to find the number of milligrams m of morphine that is in a patient's bloodstream 8 hours after the drug has been administered. Okay. What was the initial dose? 10, good. And 10, yes, milligrams. We know it's 10 milligrams because 10 is that first number. This is our initial value. Next one says, how many milligrams will be present after 1 hour? How much will be present after 4 hours? Where are we plugging that 1 and 4? Into H. So let's first plug in. So I'm going to rewrite the problem, the equation. We're first plugging in when H is equal to 1. So M of 1 is equal to 10 times E to the power of 0.173 times 1. Plugging that into your calculator, you should get 8.41 milligrams. And then plugging in when H is 4. So we're plugging in 4 now instead of 1. We should get 5 milligrams. Which makes sense because our rate value is negative. Since our rate value is negative, we are going to be decreasing over time. So we started with 10 milligrams. After 1 hour, they have about 8 milligrams. And after 4 hours, they have 5 milligrams of morphine still in their system.